So answers to forces quiz number 3. So on your test, you can expect an Atwood machine, and in fact, later on today or next class, I'm not sure, I'm going to be giving you a practice Atwood machine with some nasties as well. The whole goal is you find the homework and the quizzes tough. You hopefully find the tests easier than the homework and the quizzes. If I'm doing my job right, that's how it works. It says, given the following massless, frictionless pulley Atwood machine, where M1 is 21.3 and M2 is 19.6, find the acceleration. I notice those weights are really, really close to each other. If the weights were identical, what would the acceleration be? Do you remember? 0. I'm expecting a pretty small answer, right? If the weights are really, really far apart, I'm expecting a bigger answer. Although, what will the answer never be bigger than here? Because if I had only one weight in free fall, that would be 9.8. If I've got another weight in the opposite direction, slowing it down, even a small weight, you know what? It's got to be less than 9.8. So there's some built-in error checks. What are the forces acting? I'm pretty sure I got M1G, tension, M2G, tension. Now this isn't technically a free body diagram because you'll notice I didn't try and get tension bigger or smaller based on where I put the arrow. Riley, if I'd said draw the free body diagram, I would probably say, well, for mass 1, I know gravity's winning, tension's losing. For mass 2, I know gravity's losing, tension's winning. I'd probably draw it something like, if I actually asked you, draw the free body diagram. And probably on your test, you can expect me at least once to ask you to draw a free body diagram. But if I don't say draw a free body diagram and you have a lovely picture in front of you and you just want to label the forces on the picture, knock yourself out. Go ahead. You're going to have to concentrate and write the test with me talking. Suck it up and live with it, kiddo. Oh, he is concentrating. Good. Oh, now he's not. Go back. Who's winning? I'm pretty sure M1G, which means tension is a loser. But it means that other tension comes across. It ends up being a winner. Yes, yes, yes. Minus a loser. And since I've looked at more than one mass, it's mass 1 plus mass 2 times A. Tension vanishes. Jordan, how would I get the A by itself? You did it right. So yeah, how would I get the A by itself?
Divide M1 plus M2.
Yeah, divide by the bracket. So if I hear you correctly, my friend, you're saying acceleration is going to be M1. Bear with me for a moment. Interruptions, but that's okay. This goes online anyhow. It's going to be M1 G minus M2G divided by M1 plus M2. It's going to be, M1 was 21.3, 9.8 minus 19.6 times 9.8, all divided by whatever 21.3 plus 9.8 is. 19.6. Wow, boy, I'm looking at the wrong thing or what? Thank you. I wish I'd done that on purpose to see if you're paying attention, but that was just my brain being stupid, which happens far more often than you guys realize. I wrote that. Am I going to use brackets for multiplication on my calculator, Jordan? Heck no. I'm going to use the times sign. I'm going to put a bracket at the beginning and the end of the top and a bracket at the beginning and the end of the bottom. But that's probably the only brackets I'm going to use in this particular equation because I find too many brackets, I get confused. If I did this, if I went 21.3 bracket, just by doing that, now I've told my calculator that everything else is no longer on the top because I've closed the top off. So it's bracket 21.3 times 9.8 minus 19.6 times 9.8. Close off the top. Divided by 21.3 plus 19.6. Close off the bottom. You get 0.407334, 0.407, let's say. Yeah? Units? Okay. Now if you got that, you get 4 out of 4. Otherwise, in terms of part marks, I would give you 1 mark if I saw that, 1 mark if I saw that, 1 mark if I saw that, and 1 mark for the answer. Yes? Yeah, you lose a half mark if for not putting the units. Which the moral of the story of that is before you hand in any test, what do you quickly double check? Units for the written section. And technically sig figs. If you said 0.41, I'll take it. It is, I think, though, technically 3 sig figs, and that 9.8 that we use is actually 9.80. It is as many sig figs as we need because it's a constant. Find the tension. Go look at one mass. Which mass? I'm going to choose the one where tension is winning because it's easier, so I'm actually going to choose mass 2. I will do it both ways for you, though. If I go with mass 2, my equation is going to be tension minus mass 2g equals mass 2a. My equation is going to be tension equals mass 2a plus mass 2g. It's going to end up being mass 2, 19.6 times a, I'll use my answer button, plus mass 2 times g. You get a tension of 200? 0.1, 200? Yeah? So I'll go 200 newtons. Technically, you should put a dot there to go 3 sig figs. If you didn't, I'm not going to freak out. If you used mass 1, you would go M1G minus tension equals M1A. You would say tension equals M1G minus M1A, which ends up being M1, 21.3 times 9.8 minus 21.3 times 0.407334963, also 200. Half mark off for no newtons. In terms of part marks, I would give you 1 mark if I saw either equation, 1 mark if I saw that, and then 1 mark for the answer. Hey, you finished the test early. Could you try finding tension both ways just to see if you're right? Sure. Double check to make sure you didn't make a calculator mistake, right, Jordan? Built in. All right, now we're skiing. A 47 kilogram cross-country skier is moving horizontally over packed snow. Coefficient of friction between the snow and the skis is 0.11. What force is required to keep the skier moving at a constant speed? I guess, how hard does the skier need to push on their ski poles? Okay. Looks like a job for a free body diagram. There's my skier. Hey, what are the forces acting on the skier? Get the obvious ones. And since they're not sinking into the snow, normal force. Now, there's a reason, McKenna, I said horizontally. In Physics 12, we'll redo much of this unit, but partway through we're going to ask a simple question. We're going to say, what if you're on a hill? What if you're on a ramp? And then the normal force is no longer equal to mg. Then you're going to bring in lots of trig and lots of math. So just beware. This is why, Callum, I always say, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What I'm trying to teach you, Riley, is look at your free body diagram. Oh, and by the way, in Physics 12, as soon as we're on an angle, we're also drawing a free body diagram right away, too. And it'll be different. I think there is an applied force pushing them forwards. And I think friction is slowing them down. Who's winning? I guess that's kind of a trick question. Actually, isn't it a tie? How do I know it's a tie?
In order to go at a constant speed,
Yeah. I mean, he's moving to the right, but that's Newton's first law. He wants to keep going, because I think the net force on this skier is 0. So Newton's first law says he wants to keep going in a straight line at a steady speed. I would have no problem if you said, by the way, F applied is the winner, if you did this. But I hope you would have said equals 0, because the A is 0, yes? Equals MA, but A is going to be 0. Right? How do I know 0? How do I know that? 2 words that I underlined. Constant speed. That's a that's one of the physics trigger, right? At rest, another physics trigger word you've spotted, but constant speed, another one, right? So you actually end up with the applied equaling friction. This is why I said it's a tie. They're tied. So the applied is going to be, friction is mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force, mg. It's going to be 0.11 times 47 times 9.8. 50.666, so 50.7, 51, and it's a force, so it's got to be newtons. In terms of part marks, I would probably go something like this. I think I would give you 1 mark if I saw a good free body diagram. I would give you 1 mark for getting that equation, or if you jump straight down to the middle, that's fine. And I would give you a half mark if I saw that, and a half mark for the answer. Oh, something like that. And then I would turn the page. It says, consider the 12 kilogram mass below. What would be the acceleration of the mass? Assume there is no friction. Oh, who's winning? Really? Yes, the 60. So if I want to use my tug of war, I can go 60 minus 36 equals my net force MA. I can do 60 minus 36 in my head. 24 equals MA. So A is going to be 24 divided by the mass. 24 divided by 12. Did this work out evenly? It tells you probably Mr. Kamosi made this up because he's willing to crunch numbers and do math in his head to make them work out nice. God bless him. If it's a decimal, usually means I made it up because I'm too lazy to do that. And I think the real physics world is messy and you get decimals. Shut up and deal with it. Like when you guys round it off, or hey, so deal with it. Yeah, sure. Number 4. If the applied force is 225 newtons, and by the way, these are a pain to draw using Microsoft Word. So often what I'll do, and number 4, I like this question, like this question, like this question, like this question. Often what I'll do, I'll give you the generic diagram, and then in the question, I'll tell you what the applied force is, what the coefficient of friction is, and what mass 1 is, because it's easier than trying to actually put the numbers on the diagram. If you've ever done graphics in Word, that's a pain. So make sure you read the question carefully. Draw a free body diagram. Gravity down. Normal force up, same size. I'd be looking for 2 arrows the same length there. Here's the applied. Friction. How many arrows did I draw? How many marks is this worth? What would a good scale be for each arrow, do you think, in terms of what it should be worth? Each arrow is worth a half. Now, if you have friction the same size or longer than the applied, I'd take it a half mark off.
How did you know not to draw friction the same size? How do you know it wasn't a tie?
Because I looked at B and I said, oh, there's apparently an acceleration. That's not physics, that's just good test writing, right? I clued in. And I assumed the acceleration wouldn't be 0 because that'd be kind of a boring question, especially because we just did one where the acceleration was 0. Duick probably would set up a better quiz than that. Again, not physics, but good test writing. Find the acceleration. Who's winning? Vertically, everything's tied. Horizontally is where we have our unbalanced force. Winner minus loser equals MA. The applied force is 225 minus friction is mu times the normal force. I don't know the normal force. Oh, but look. Anyways, equals, oh, and to get A by itself, I would divide by the mass. I'm going to get 225 minus mu, which was 0.15. Friction is, sorry, the normal force, I don't know, but it's the same as mg, so it's going to be 100 times 9.8. It's 1 times 10 to the 2, but that's 100, which is less writing. I don't know why I typed 1 times 10 to the 2. I'm guessing I was modifying a question from your test. Oh, never mind. Oh, I think I said I like this question, Like, did I? If I didn't, I just did. Divided by the mass of 100. Jordan, bracket right there, and then it's going to be 225 times 0.15. No, not times, minus, Mr. Duick. 0.15 times 100 times 9.8. The reason we don't need to add extra brackets and stuff, when you're doing it by hand, you have to do bed mass properly. Your calculators, did I go on a rant at the beginning of the year about getting a half-decent calculator? If you have, they all do bed mass for you automatically. My calculator will multiply and then subtract. Yes?
You accidentally got rid of the 1. You was 0.5.
I actually got rid of the 1.
In the 1.5? In the calculator.
Oh, in the calculator? Thank you. insert typo. Like I said, calculator errors. Close bracket, divided by 100. You get an acceleration of 0.78. Not much acceleration, but is it 0.78? Yep. So if I was actually being fussy, and I won't be, but if I was being really, really fussy on my free body diagram, this should only be just a little bit longer than friction, technically, because it's barely winning. How do I know it's barely winning? That's a pretty small acceleration. But I like to exaggerate in my free body diagrams because I find that helps me really see what's going on, so I'm good with that. In terms of part marks, I would probably go something like this. Half mark if I saw that, half mark if I saw that, a half mark for sticking in numbers, and a half mark for the answer. And if you could give yourself a lovely, lovely score out of, count 'em, 15, that would be awesome. So looking at universal gravitation, we said that you can calculate the force of gravity between any two objects in the universe by multiplying their masses together, m1 times m2, dividing by the distance between them squared. Oh, but that gives you an answer in kilograms per meters squared. To get it into newtons, you needed a conversion factor. We used the capital letter G, big G, and it turns out to be 6.67 times 10 to the negative 11. It's a really, really small conversion factor. It's the universal constant due to gravity. That constant is the same anywhere in the universe. That conversion factor is the same anywhere in the universe. And we calculated the force between two 4-kilogram masses. And we calculated the force of gravity between the Earth and the Moon. And then we asked ourselves questions about how would this behave if you doubled the distance, tripled the distance, halved the distance. We said for the distances, AJ, closer means stronger, further means weaker, but it's the ratio squared. So if you triple the distance, if you're 3 times further away, it's not 3 times weaker, it's 9 times weaker. By the way, that's called the inverse square law. And Jordan, that is true of anything that radiates out. So for example, sound obeys the inverse square law. See where Sean is? See where Jordan is? Jordan's about twice as far away from me as Sean is, roughly. Jordan hears 1/4 the volume that Sean does, roughly. And you're about twice as close as Sean is. You would hear, I'm 4 times louder to you, and compared to Jordan, who is 4 times further away, I'm 16 times quieter back there. The inverse square law. Thermostats, heaters work the same way. So radiant heat, if you go twice as far away from the heat source, you're only getting 1/4 as much heat. That's why you take 1 step back away from a nice warm fire by a campfire. You're like, oh, I'm noticing that. Or you really notice it if you go close enough so that it's almost uncomfortably warm with your hands by a campfire, and then go twice as close. You'll go from uncomfortable to burning pretty quick. Okay? Anything that radiates follows the inverse square law. Not that you didn't know that, but nerdy physics moment. And we paused right here. So we said this. Gravity is usually minuscule, usually really, 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 really small.
Can we do the other question, please?
Can we do the other question? Oh, G? Sure. Sorry, I forgot about that. If we double both of the masses and we double the distance. So if we double the distance, that's going to be 4 times weaker, right? We would describe that mathematically, AJ, as force divided by 4. What if we double the mass? Twice as strong. What if we double both masses? Okay, 4 times stronger. So if doubling the distance makes it 4 times weaker and doubling the masses makes it 4 times stronger, if you do both at the same time, what's your net result? Yeah, they cancel out. You just end up, thanks AJ, I forgot I hadn't done that one. You just end up with the same force F. Yeah. Is that okay? Now let's turn the page. Gravity is usually pretty minuscule unless one of the masses is huge, like a planet or a star or the moon. The moon has enough mass, it sloshes the tides back and forth. It pulls on one side of the Earth the oceans towards it, and on the other side of the Earth, it pulls the oceans inwards a bit, which gives you the oceans sloshing back and forth on a vast scale, the same way if you hold a bowl of water and you slosh it back and forth, there's a wave that travels back and forth. Tides. Example 4. Assume the mass of the Earth is 5.98 times 10 to the 24th. It is. And its radius is 6.38 times 10 to the 6th meters. It is. Find the force that the Earth exerts on a 50-kilogram person on its surface. Now, instead of using d, because we're talking about the radius of the Earth, I'll use r squared. Now, some notation that we start using in Physics 12. Instead of writing M1, M2, what we'll sometimes do is this. Big M, planet, lowercase m, person, satellite, moon, whatever's orbiting. I'll flip-flop between the two, but just to get you used to it right now, this time, I'll write big M, little m. Oh, let's see if we can crunch the numbers here. G is this gravitational constant of the universe, 6.67 times 10 to the negative 11. Big M is the mass of the Earth. Now, this is on your formula sheet, by the way. I made sure to include it. And it's also in your notes on the very, very last page. But for now, I also gave it to you in the question. It is 5.98 times 10 to the 24th. Second mass, mass of the person, 50, divided by the radius of the Earth. Now, it's technically the distance between the center of the Earth and the center of mass of the person. But Tanisha, since the radius of the Earth is so huge and the height of the person compared to that is so small, I'm not going to try and include the height of the person. It's not going to make a difference. That's that little note I wrote there in brackets. You can ignore the size of the object when you're comparing it with the radius of the Earth, because the Earth is so huge. What's the radius of the Earth? 6.38 times 10 to the 6th. And that number is squared. Once again, you probably want to practice with your calculator. Try crunching this number and see what you get. Ideally, you should get, I think it's 489.99 or something like 490 or close to it. If you didn't, now is your chance for me to come help you with your calculators. So I wrote here, it shouldn't be surprising, because if we calculate the force of gravity using just mg, we also get 490. But here's the nice thing now. Now that I know that it works on the Earth's surface, it means I can be reasonably confident that it'll work in orbit, or on another planet, or wherever. I can be confident that it's universal, which is why we call this universal gravitation. Turn the page. Jordan, we have something called the gravitational field of a planet. We give the gravitational field strength a symbol. We give it a lowercase g. You actually already all know this one. What's the gravitational field strength of the Earth? Sorry? No. You know this. What's the gravitational field strength of the Earth? We've been using the, what have we been putting in when we see a little lowercase g? Okay. I should be careful. That's the gravitational field strength on the surface of the Earth. See, now we're going cosmic, we're going orbital. The further you get away from the Earth, what happens to the Earth's gravitational field strength? What happens when objects with masses get further and further apart? Okay, it's going to get less. Now, this is not a force. What were the units for g? Meters per second squared, because it was an acceleration. Or, because it's an acceleration, isn't it also newtons per kilogram? Because it's force divided by mass. That would also have to be the same as acceleration, yes? Because F equals ma. We say the Earth has a gravitational field. How strong? 9.8 newtons per kilogram. We usually say meters per second squared when an object is in free fall. When we're talking about the force of gravity, we say it pulls with 9.8 newtons on every kilogram of mass. And we can calculate it. There are two ways. The second way, down here, we did a while ago. The second way is to drop an object and time it in free fall. Remember, we dropped erasers and stuff from the stairs there, and we had errors in our instrumentation, but you could agree with me, we could have, if we had better equipment, got that 9.8 pretty accurately by having VI equals 0, measuring the distance, and timing how long it took to hit the ground. Right? Yeah. There is a second way. The second way you can calculate the gravitational field is to use a scale. This is what gives you the newtons per kilogram. If you use a calibrated spring scale like this, I think I have one. So the first way that we could get this is to hang a mass from a scale, right? It can be determined by measuring the weight Fg on a small test mass. This is just hang a mass or drop something in free fall. There's a problem with both of these methods. The problem with both of these methods is you have to be on the planet to calculate its g. If I wanted to drop something in free fall on Mars, I have to be on Mars. Yes? Or if I want to hang a mass from a scale on Mars, I have to be on Mars. But I'm going to tell you right now, we were able to calculate the gravitational field of the moon before we went there. We were able to calculate the gravitational field of Mars before we started sending probes there. We had to. Otherwise, we wouldn't be able to land there in the first place. We wouldn't know how strong to build the rockets. How did we do that? How are we able to calculate the gravitational field strength anywhere in the universe without actually going there? Johnson, there's a third method. And it comes out of the fact that we were able to do this. It comes out of the fact that we can calculate gravity on a planet like this, but we can also calculate gravity on a planet like mg. It comes out of this idea here. The fact that I think I can safely say, McKenna, that gravity equals gravity. Anything wrong with that? No. But we have two ways to calculate gravity. The easy way on the surface of the Earth and the universal way. Big G, big M, little m, over r squared. Those have to be equivalent. How do I know? Because I got 490 on the previous question, the same answer, both methods. Yes? Ah, but Amanda, do you see it? The tiny mass turns out to cancel. And what I'm left with is now a formula for calculating G. Not dropping an object and timing it, not hanging a mass from a scale. This gives me a formula so that I can calculate G without actually having to go there. How can I calculate the gravitational field anywhere in the universe? It's equal to big G, which is not gravitational field, that's the conversion factor, Newton's universal constant. The mass of whatever planet, moon, Mars, whatever, divided by the radius of that planet squared. We can calculate the gravitational field strength of the moon by going G, 6.67 times 10 to the negative 11, times the mass of the moon divided by the radius of the moon, squared. We can calculate the gravitational field strength of Mars the same way. And we needed all of those before we started sending probes there. Yeah?
How would they find the mass?
What a great question. Michael, can you ask that again?
How would they find the mass of the planet?
We'll be back. So, if we compare these two methods, we find another way to determine the gravity field. This guy here, gravitational field strength. let's write this. Gravitational field strength is big G, big M over R squared, where little g is by the way, if you put in the mass of the Earth and you divide by the radius of the Earth squared, you know what you'll get as an answer? You all do, because you know the answer. What is the gravitational field strength here on the Earth? Yeah, you'll get 9.79999 and 9.8. So that now you got a third way to confirm that this equation does seem to work, because you have a measured value and it matches the theoretical calculated value. Michael, can you read this little bullet right here?
This last property is useful because it provides us with the means to calculate the mass of the Earth.
Since you asked. The mass of the Earth was a matter for great debate for centuries, because you can't put the Earth on a scale. The radius of the Earth had been known for about 2,000 years. There's all sorts of ways to calculate the Earth's radius. You can use geometry and the sun's rays. A Greek mathematician named Eratosthenes did that about 2,000 years ago and got a pretty good estimate. I think he was accurate to 2 or 3 sig figs. Not bad for Roman numeral drawing math. Or you can, if you watch a ship sail off and vanish over the horizon, if you know the height of the masts and you know the distance to the horizon, it's pretty easy to figure out what kind of curvature you're dealing with, and then just extend that curvature, and lo and behold, you got the radius of the Earth. That's all doable. You can spot the shadow of the Earth on the moon. Calculate the radius, all sorts of ways. We knew the radius of the Earth. And that whole Christopher Columbus thing, thinking the world was round, that's a myth. Don't believe that. Thinking the world was flat, don't believe that. They knew the world was round. But there was a lot of debate as to what the mass of the Earth was. The best guess at that time was to calculate the volume of the Earth, and if you know the radius, you can get the volume. The volume of a sphere is 4/3 pi radius cubed. And then multiply it by what you thought was the average mass of a rock. There's a problem. That assumed that the Earth was the same density all the way through. Okay. Seemed like a reasonable assumption, because when you dig down, what do you run into? Rock and dirt and rock and dirt and rock. And certainly 300 years ago, there weren't holes that were all that deep, rock and dirt and rock and dirt. So you would say, this is about an average mass of rock and dirt. This will give me a rough estimate. Volume times density gives me mass. Remember I said finding this G, this 6.67 times 10 to the negative 11, was very, very difficult. Cavendish did an experiment to find it. As soon as he found that, one of the first things he did, Michael, was this. He said, well, I know the radius of the Earth, 6.38 times 10 to the 6th. And I know that I can calculate gravitational field strength to be that. Right? We're not talking newtons now. We're talking gravitational field strength, which is the same as acceleration. It's meters per second squared or newtons per kilogram. He said to himself, I just found this, proud I am. I know this. I know that's 9.8 because I've dropped stuff and timed it. Can I not now cross multiply and find the mass of the Earth? Wow. Finally. Wow. 300 years ago. Wow. So they did. Get the m by itself. It's going to be g r little g r squared divided by big G. Yes? Right, the r stuff moves diagonally, Perry. The r squared moves to the top, g moves to the bottom. Little g, 9.8. Oh, and mass is a scalar, so we're not including directions like negatives or anything, Kenny. Radius of the Earth, they had calculated that a long time ago, 6.38 times 10 to the 6th squared. Cavendish had just finished calculating. Oh, not 5.9, Mr. Duick. G is 6.67. Times 10 to the negative 11. Crunch that and see if you get the mass that I gave you for the Earth earlier. So the mass that I gave you for the Earth was 5.98 times 10 to the 24th. See if you get that. Also, good calculator practice. If you haven't figured it out, by the way, one of the most common mistakes on the gravitation section in this unit on the test is calculator errors. So where is your calculator? You're missing out a chance to practice. 5.6 you should get 5.98 times 10 to the 24.
I have the exact same thing with him, so.
I think you typed it in wrong. You're going to go 9.8 times 6.38. Scientific notation button 6. Oh, I should have put that in brackets. 9.8 times, because I want to square this thing, 6.38. Scientific notation button 6. Square that. Divided by 6.67. I'm pretty sure I get 5.98 times 10 to the 24th, he says smugly. Now here's the problem. That was wrong. Sorry. That answer, based on all of the previous answers that people had been using, was way too huge. Cavendish checked with his other nerdy scientist friend. I've crunched the numbers. I'm getting this, but the number that we've calculated using that volume times the average density of the Earth gives us a way smaller answer. What does that mean? The Earth doesn't have the same density all the way through. Now, you guys have done some science and some Earth science. You have some advantage over Cavendish. What's at the center of the Earth, folks? I heard someone say it. Magma, not magma. A big iron core. How do we know? Because this number is too big if it was all rock. This was one of the first things that started them thinking, hey, you know what? It can't be dirt down there, because if it was dirt down there, it wouldn't weigh this much. There's got to be something denser than dirt down there. There's other things that tumbled them onto the fact that it's iron, the fact that the Earth has a magnetic field, and a few other things. But certainly this was their first way of saying, you know, I don't think it's just dirt all the way through. It took a few years, few decades for that to kind of percolate through the scientific community and convince them. But yeah, sorry? What did somebody say? It's to this day, we know far more about stars millions of light years away than we do 6 miles below us. We know very little about what's below us. Very little. In fact, there is a big oil. Where does oil come from? Yeah, William. Where does?
Something sphere.
But what is oil from?
Decayed plants.
Says you. Okay, there is a movement right now. There is a big movement right now that is suggesting that oil is actually created by bacteria down in the Earth, not by decayed fossils. And it's gaining ground. It may be wrong, but you understand, something as basic as we're not sure, because we weren't there, and we really don't know that much about stuff below us. Earth science is barely in its infancy. You guys learned in Science 10 plate tectonics, which seems very obvious, especially when you look at a globe and see how the continents all kind of fit together. Okay, 50 years ago, you would have been laughed out of any university for suggesting that. Your grandparents and your great-grandparents would have thought you were witches and witchcraft and stupid. Earth science is a fairly young, very undeveloped science. Anyways, since you asked, now that we have the mass of the Earth, haha! We could probably come up with an equation by figuring out the moon's gravitational force. And since we know the mass of the Earth and we know the forces of the same, hey, now we can get the mass of the moon. Aha! Hey, now that we know the mass of the Earth, we can probably come up with an equation to see how the sun affects us and our gravitational force. And we can cross-multiply, and now we can find the mass of the sun. Nice. Ooh! Now that I got the mass of the sun, I can start whittling away. This was one of the dominoes, and you can start whittling away at the planets and all sorts of stuff now. Homework. Try number 1. Try number 2. Try number 3. Number 4. Now, number 4 is tricky in that, what's the word that's in bold font? That means that the distance from the center of the Earth is that number plus the radius of the Earth, because above is only from the Earth's surface. So when you're going F equals big G m1 m2 divided by r squared, your r is going to have to be the altitude plus the distance from the center of the Earth to the Earth's surface. Number 5. 6. 7 is good. 9 is good. It's going to seem like a lot, but next class you're not going to be getting any new homework. Oh, by the way, it says find using your data sheet. Here's your data sheet that has all the numbers that you need on the next page, right? We can do, so far, there is no 8, I know. I nuked it. Sure, 10 is good, 11 is good. "12 is good, but please notice they gave you the radius in kilometers. You'll have to change it to meters. And I'm going to pause with that. You can work on it, but you'll get all next class to work on it as well. Yep. Yep. Okay.